So in the previous class, we have learned about the equations used in electrodynamics. Okay. So you have learned the wave equation, which is satisfied by the scalar and vector potentials A and phi. A and phi. Okay. Both these potentials, vector potentials and scalar potentials, satisfy the inhomogeneous wave equation. Inhomogeneous wave equation, that means grad square or box square phi equals to minus rho by epsilon naught, and grad square A is equal to mu naught z. These two are the inhomogeneous wave equations. Okay, and this inhomogeneity in the differential equations arise due to the extra source term. This rho and z, this rho and z, these are the source terms. Okay. So in the absence of source term, the wave equations will lead to the common wave equations, which are homogeneous wave equations. But in the presence of the source terms, external source terms like rho and z, uh, the Lorentz gauge and Coulomb gauge solution of phi and A will satisfy these inhomogeneous wave equations. Okay, or explicitly, you can write grad square minus 1 by c square del 2 del t2 of phi. Phi will be function of rt is equal to minus rho function of rt by epsilon naught. And similarly for z, that means for a, del 2 del t2 of a being function of space time is equal to mu naught z. J will be function of space. So these are the equations satisfied by the potentials phi and A in arbitrary situation. Okay, the sources are function of space time as well as the potentials the function of space. But you have initially studied the special case. Special case means electrostatic. Electrostatic and magnetostatic. These two cases. Magnetostatic So, in general, in the electrostatic case, this inhomogeneous wave equation of phi will lead to the normal Poisson equation, which is grad square phi is equal to rho by epsilon naught. In general, this phi will not be the function of time; it will be only function of space. Rho, and also the sources will be static source. So that's why it's not the time varying one. The rho r by epsilon. So this is a special case of this equation where the source is static. So this is electrostatic case. Okay. So similarly, for magnetostatic case, if A is not the function of t, is static A with time, then you can write grad square of A is equal to mu naught z. Okay. So at first, we shall highlight on the solution for phi and A. That means for electrostatic case, we have to find the solution of these equations. And you know, these equations are generally known as the Poisson's equation. The special case is Poisson equation. Okay. So in the name of Poisson equation, there is a homogeneity. Sorry, there is a inhomogeneous terms due to the external source. Rho and Z, these are the external sources, and under these sources, uh, the dynamics of the potentials will be governed by this Poisson equation. And if you nullify the sources in the absence of source, in the absence of source, that means rho equals to 0, Z equals to 0, this equation will lead A equal to 0. These are called Laplace equation. Okay. So Laplace equation, it's very easy to solve, relatively easy to solve, and you can find the solution from the complementary function solution. This is the homogeneous part or homogeneous version of the general Poisson equation. Okay. So these are the known these have the known techniques to solve this equation, the Laplace equation. But inhomogeneous equation can be solved in a particular way, and one of these particular ways are very common, and the technique is green function technique. So in general, we can take a inhomogeneous differential equation, which is suppose some function of grad to the power n, grad to the power n minus 1, and some also function of r square is equal to sorry, in general, any uh, inhomogeneous differential equation can be taken as some function of operators and the algebraic terms like grad square, or in general grad n, grad n minus 1, and all of these over function of fr is equal to dr. So this is the common form of an inhomogeneous equation. Common form of an inhomogeneous equation. For example, our Poisson equation. Poisson equation is, suppose in generally I am writing grad square of fr equals to gr. Okay, this is the example which is Poisson equation. Okay. So how can you solve this equation? Okay, how can you solve this equation? So in one dimension, let's start with one dimension. In one dimension, you can write this is function of del n del xn del n minus 1 of del x n minus 1 over some f of x equal to gx. So in one dimension, the form of inhomogeneous differential equation is like that. Okay. So this is some function of operator and function of differential operator basically, and it can take as a whole as a operator. Okay. So suppose this is the d operator, dx over fx is equal to gx. dx means all of these things, the function of operators and the algebraic terms. For example, in one dimension, you can write del 2 fx by del h2 is equal to gx. So this is the one dimensional Poisson equation. And in this case, the dx, there you, if you compare, the dx is nothing but del 2 del x2. Del 2 del x2 operator is the dx. Uh, so in general, you can write in one dimension the general form of an inhomogeneous differential equation. Okay. So clearly, you can transform this equation or the expression of this equation in the abstract form. You can transform this equation in abstract form. Abstract notation, it is the general notation. Okay, abstract means here general. Abstract representation abstract representation is the general representation. Okay. You know that any function can be represented in different representation following the quantum mechanical wave function. You have already learned that. Suppose the wave function can be represented in position representation, in momentum representation, in energy representation, in any arbitrary operator representation or observable representation. Okay, you can represent the wave function as psi a, any sort of representation. But Dirac generalizes this representation and he introduced a general form of representation which is the abstract representation, or it is known as the bracket representation. Dirac bracket representation. So in Dirac bracket representation, all sorts of representation you have done in different cases in quantum mechanics can be taken in one form or in one algebraic or one representation term, which is psi ket. This is called ket vector. So this includes all of these representations. Okay. So any different representation psi x, phi p, chi e, or anything is related to psi ket. And here, if you want to find suppose psi x from psi ket, you have to make the inner product of the representation basis, their position basis, with the ket. Okay. And if you want to find phi p, this will be p psi. If you want to find chi e, that will be suppose the basis, Hamiltonian basis with psi, and so on. So this is the way of generally representing any function in the ket notation, and this notation is known as the abstract notation. Okay, এবারে বোঝা গেছে তো? এবারে বোঝা গেছে?
Yes, sir.
Okay. So this is the general way of representation. It is called the abstract representation. Now try to represent this equation, this dx of fx, in terms of abstract notation. Dx of fx equal to gx. So I am denoting the operator, abstract notation operator is suppose dx cap. Okay. So dx will go to dx cap. Fx will turn into get f and gx will turn into get z. This is the transformation you can do to represent in the abstract notation. So here this is dx cap of f equal to, so the equation has been taken in the abstract notation. Now in order to solve this equation in abstract notation, dx must be invertible operator. Invertible operator. Okay. Operator. What is invertible operator? What is invertible operator? Hmm? Inverse possible. Hmm. Ah. The inverse matrix of dx must exist. Okay. D, suppose this is denoted by d inverse x. Exists. This is called the invertible operator. So generally in quantum mechanics or in any laws of physics you have studied so far, all includes the invertible operators. Okay. So dx equals to z. So what should be the solution of this equation? What should be the solution? So f is equal to, you can directly write d inverse z plus some integration constant, because this dx is differential operator. So you can directly write f equal to that plus some h I, or in general you can take the summation of all of these. So summation over I ci into state of hi. So this hi are such functions that it will satisfy uh, dx of hi equals to 0. So this is the general solution from here. Okay, এটা বোঝা গেছে কি করে লিখলাম?
স্যার এটা
হ্যালো, আমি বলছি এই তো ইকুয়েশন ছিল dx of f equal to z. Now what should be the solution? In general you can write f equal to dx inverse of z plus some constant should be there. Okay, actually not constant, actually independent of this dx operator should there. Okay, কারণ তুমি রিভার্সটা করে দেখো, মানে এর বোথ সাইডে তুমি dx অপারেট করো তাহলে কি হবে, এর বোথ সাইডে তুমি যদি dx অপারেট করো তাহলে কি আসছে, dx of a equal to dx of dx inverse of z plus summation over I ci dx of hi. So this is 0, this is I. So এখান থেকে আমরা এই জিনিসটা ফেরত পেয়ে যাচ্ছি, তাই না? কারণ dx inverse, this is I. ওকে, তাহলে এর জেনারেল সলিউশন কিন্তু এটা, মানে এই পার্টটাও থাকবে অ্যাকচুয়ালি, কারণ এরকম কিছু ফাংশন থাকবে যারা এই জিনিসটাকে স্যাটিসফাই করবে। সো অল অফ দিস থিংস শুড বি ইনক্লুডেড হিয়ার। এবার বোঝা গেছে না বোঝা যায়নি?
হ্যাঁ স্যার বলুন।
ওকে, সো নাও the general solution is equal to of z plus summation over I ci h, and this h will satisfy dx of hi equals to 0. So this is the homogeneous part of the equation, dx of hi equal to 0. So you can say that HI are the complementary function. HI are the complementary function, and you can fix the coefficient Ci from boundary condition. Ci's can be fixed, from boundary condition. So HI is the complementary function part of the solution. You know, in homogeneous differential equation, you have two parts, two fragments of the solution, and their linear combination or their sum basically will yield the complete solution. So here this CIHI part is identified as the complementary function because it satisfies the homogeneous portion of the equation. Okay. And now this part, the d inverse x of g, this is particular integral. This part is particular integral because this is completely dependent on the inhomogeneous source. G was the inhomogeneous source in this equation. In the absence of G, the equation will turn into the homogeneous equation. So the complementary function was due to the homogeneous part, but the particular integral part, it is purely due to the inhomogeneous source. Okay. So if you avoid the source, this part will be 0. So this is particular integral, and it is based on the external source G, or external inhomogeneous term in mathematics. Mathematically, you can say this is particular integral. Okay. So we have identified the parts of solution, but of course it is not the original equation. The original equation was in terms of the spatial representation or position representation. We have turned it into the abstract notation, and in abstract notation we have found this. Now, ideally, you can turn it into the position representation by making some inner product, or taking inner product with the position basis. So, x of f is equal to x of this one and summation over I of x of h. Okay. And as per the definition of abstract notation, you can write this is fx equals to this is x dx inverse d plus summation over I ci into hi. So this part is complementary function. So in general, from transforming from the general notation or abstract notation, you can find it in your original representation, which was in position like that. Okay. Now this portion, you can introduce some unity operator here. Suppose this is Ig plus this is complementary part. And in Hilbert space, that means continuous basis set. Continuous basis set. In continuous basis set, what is the form of I? Integration minus infinity to plus infinity dx x, right? So dx is the definite integration over dx, so you can take prime over there, because at last, at the end, you have to put the limit of x prime. So whether it be x or x prime, it does not matter. Dummy index, here I is dummy index, so integration x is dummy. So here also then you can write fx equal to integration of dx prime, then x g, sorry, x g x prime, sorry, x dx inverse of x prime of z plus some complementary function part. So this one is x dx inverse x prime g of x prime plus complementary function. So the general solution of an inhomogeneous differential equation is like that. Okay. And this, what is this? This portion. Can you identify this one? This is nothing but the matrix element of dx minus operator, dx inverse operator, x prime. Okay. Because you know the matrix element of operator mn is m o n. So thus x dx inverse x prime, it is nothing but the matrix element of this operator in the matrix representation, in the basis, in the position basis representation, of course, because I am writing the basis from position representation x and x prime. So ideally it is integration dx prime dx inverse of x prime e of x prime plus complementary. And this particular term is known as the green function x prime. This is known as the green function. So I should write it in green. So at last you can summarize the solution. Suppose I am writing the original equation again. The original equation was dx of fx equal to gx, and the solution will be fx equal to, suppose, a complementary function x, complementary function part, plus integration dx prime g x prime gx prime. So this is the complete solution. Now suppose you are given a equation like that, okay, you will solve, you can directly write the solution in that way without thinking further. You can write the solution in this general way. Fx equal to the complementary function. Complementary function can be solved by taking it to be 0, and then this additional term which is particularity, and this gx prime is the, it's known as the green function. Okay. And in 3D, okay, in 3D, suppose this is e function of fr equal to gr, and identically you can put the solution for fr is equal to f complementary function part plus integration of, it is volume integration dr vector prime g r prime g of r prime. So you can directly write the solution in terms of the green function like that way. Now your next job is to find the green function. Your ultimate or next job is to find green function z x prime or g r prime in 3. Okay, because you have done the job by writing the solution, but it is not the explicit form of the solution. Okay, you have to find the terms in this equation. At first, you have to find complementary function, which you know how can you find it. And second job in your hand is to find the green function. Okay, and once you find the green function, then you can explicitly find the solution for a function. So how can you find the green function? Okay, so in order to do that, let's start with the one dimension. And in one dimension, what is gxx prime? In one dimension, gxx prime is the matrix element of this one. So this is x. So you know dx of d inverse x is equal to I. This is the definition of unity operator. Uh, any matrix and its inverse matrix can be taken, can be product with unity matrix. So dx and dx inverse will equal to I. So now dx inverse of x prime, which will be x I x prime. This one. Now you can insert some unity operator here. Unity operator. Okay. So you can write integration dx, okay, which is dx and dx prime both. Then because already you have x prime, sorry, only one integration should be there. So integration dx, then x dx x prime dx inverse, or sorry, suppose it is over integration over dx. So unity operator I have inserted in terms of suppose x. So x, so this is x prime. It is equal to, what is its value? Unity operator does not change anything. So this is x prime. So this is green function, and all of these things, this x and x again makes some unity operator and it will be gone. So it will be dx over gxx prime. This is gxx prime equals to, it will be, what is the form of sorry, xx prime. যদি এটা discrete basis হতো, that should be delta xx prime, but it is continuous basis set, delta x minus x prime. So this is so in this way, by solving this equation, you can find the green function, and once you find the green function, you can put the green function here, and you can easily solve the whole. You can easily find the whole solution for this equation. And in 3D also, in 3D it will be d of g r r prime will be three-dimensional green function delta q bar r minus r prime. This one. So your job is to at first is to write the solution in terms of green function, then find the complementary function part and fix it from boundary condition. And second job is to find the green function of that particular equation. Then you can solve this equation. Now try to take some examples. Try to take some examples. Okay, so we have started with Poisson equation. So let's try to solve with Poisson. So you know the general Poisson equation f of r equal to zr, and we have found it in electrostatics, namely grad square phi equal to minus rho by epsilon naught. And what was its solution? What was its solution? The solution is very known to all of you. What is phi r? It is very known. 1 by 4 pi epsilon naught integration rho function of r prime d of r prime by mod of r minus r prime. এটা আমরা করেছো. We have already found in electrostatics. But whatever you have taken by default is the complementary function to be 0. Okay. There from suitable boundary condition you have set this was 0. Okay. But in general case you can write it or you can put it at ICL. So this is the general solution of this Poisson equation. So in general case, that means for this one, the solution you can write is f of r will be 4 pi minus 1 by 4 pi integration g of r prime by mod of r minus r prime d of r prime plus complementary. Comparing these two, okay, this is the known solution from your Gauss's law or Coulomb's law. I have not found the direct solution from here. I have written from the physical point of view from Coulomb's law. Okay. And comparing it, okay, suppose rho by epsilon naught is zr. So here you can put rho is equal to g epsilon naught. So in this expression, if you put rho equal to g epsilon naught, then you will find minus rho minus g epsilon naught, then you will find this one. So now I am going to solve the equation directly from green function technique, and we shall try to compare the solutions from the electrostatics and the solution we shall make from the green function technique. So at first I have to write the solution in terms of green function. So f of r is equal to complementary function plus particular integral, which is g of r prime, g of r prime, d of r. So I have written the solutions. Now in Poisson equation, you can write grad square of g r prime is equal to g of r. Sorry, this is equal to delta cube of r minus r. So this is the governing equation which you can use to find the green function here. And then after finding the green function, you can put it here and then you will find the complete solution. So our scheme is to solve for this one. Grad square z, z is function of r prime, is delta cube of r minus r prime. Now try to make some coordinate transformation from r to capital R, which is r minus r prime. Okay. And here r prime is the source coordinate. R prime is source coordinate. That means where the source is put. So if you put some source at r prime, and it will act as at r. Suppose this is some. Okay, this is the source point r prime, and the effect it is here r, and this is r. So here the source is situated, and due to source, there you will find the effect I. Okay, and this delta r minus r prime, it will actually communicate between source and the test point. Okay, or basically the green function. In later part of this discussion, or in next subsequent classes, you will find that this green function grr prime will act as the propagator of interaction. In physical point of view, from physical point of view, we will find this green function will act as the propagator of interaction, propagator of electrostatic interaction. However, now we have to concentrate to solve for the green function grr. So here grad square, this is in terms of small r, as r equals to r minus r prime. So del r is equal to del r for a constant source. So grad square will be grad r square. So grad differential operator with respect to r. And here we set the natural boundary condition. Okay. The natural boundary condition at r tends to infinity, d r prime to be 0. Okay. And yeah, you can write at r tends to infinity means capital R also tends to infinity, and z r prime is also tending to 0. So the operators, the boundary conditions, all are compatible with this coordinate transformation. So may I not write grr prime to be R. Okay. R prime should be there, but how can it depend? The natural boundary condition and the operators both are satisfying and compatible with the coordinate transformation from R to R prime. So naturally you can write GRR prime into CR. So in that way you can write of R. Okay, this one. Okay. Now you have to make the Fourier transformation of GR, or you can write GR in terms of the Fourier transform. So in 3D, GR is equal to 1 by twice pi whole to the power 3 half. Suppose G tilde of K e to the power I A dot R dk. It is volume integration, so dk vector. Okay. So G tilde K, it is the Fourier transform of ZR. So that's why you can write the ZR in terms of Fourier transform. And you can put this Fourier transformed expression here, and after operating the grad R square here, so derivative with respect to R, it will yield ik and another ik, which is minus a square. So minus a square, and after that it will be 1 by twice pi whole to the power 3 half G tilde K to the power I A dot R into dk. And at the right hand side you have Dirac delta function. So you know the integral form of Dirac delta function. The integral form of Dirac delta function is 1 by twice pi whole cube into e to the power I A dot R dk. So this is equal to this particular is equal to delta cube of R. Now comparing these two, you have G tilde K, G tilde K is equal to minus 1 by twice pi whole to the power 3 half into 1 by k square. Very easy. Minus 1 by k square, and so this is the Fourier transform of ZR, that means G tilde K. Now what is ZR? ZR will be integration, of course, 1 by twice pi whole to the power 3 half into G tilde K to the power I A dot R dk. Now you can put the value of G tilde K here, and quickly you can write G of R is equal to minus 1 by twice pi whole cube e to the power I A dot R by k square dk. Okay, it's dk. Now what is dk? dk is the volume element, which is twice pi k square sin theta d theta dk. Okay, this is volume element d cube k, and theta is the angle between the k vector. This is z axis and this is suppose k vector. The angle between these two is theta. Okay. Now this k dot r is scalar, and you know under rotation scalar remains invariant. So I am taking the coordinate axis in such a way that the r and k vector are theta angle apart. That means suppose I am choosing z cap parallel to r. This is my choice because you know this will not affect the physics or physical phenomena because scalar quantity will be invariant under rotation. So whether you can choose in any arbitrary direction to be the coordinate system, it will not affect the physical result. The physical result will be same. So in order to make easiest calculation, I am choosing r to be along this direction. So this k dot r, it will be kr cos theta. So z of r 1 2 pi will be out of the integration. So 1 by 4 pi square minus integration e to the power I kr cos theta by k square into this one, this k square sin theta d theta d theta. K square and k square will be divided, and after that you have to perform the theta integration. Okay, you can take theta to be z. Suppose theta to be z, then minus sin theta d theta will be dz. So you can write 1 by 4 pi square. Integration over dk will still be there. Then it will be e to the power ikr by ikr, and the limit will be theta. The limit of theta will be from 0 to pi. So from 1 to minus 1. Okay, from 1 to minus 1. So then e to the power, okay, e to the power ikr cos theta was there. So this is the value of cos theta should be from 1 to minus 1, or the value of theta will be 0 to pi. So after performing this integration and putting the limit, you will find e to the power minus ikr minus e to the power ikr, which will be minus minus 2i sin kr by ikr. So I will be cancelled out, and r can be out of the integration. So this will be 1 minus 1 by 2 pi square r dk sin kr by k dk, and the limit of k will be from minus infinity to plus infinity. And you know the value of this integration. The value of this integration is equal to pi by 2. You can perform this integration following the complex variable integration, Cauchy residue theorem. Under suitable contour, you can find the integration, the value, numerical value of this integration will be pi by 2, and then will be minus 1 by 4 pi r. Okay, and if you put the value, you know what is r. R equals to mod of r minus r prime, because r was r minus r prime. So that's why z of r prime will be minus 1 by 4 pi mod of r minus r. Okay. So at last we have found the expression of z r prime, and this is for Poisson equation, mind it. In all equations, zr will not be same. For Poisson equation, the green function will be in that way, and hence you can put this here. Okay. You can put the expression of zr here, here. So you have f of r is equal to f of c f r and minus 1 by 4 pi g of r prime by mod of r minus r prime of d of r prime. Okay. So just resembles the equations or just resembles the solutions you have found in electrostatics, and these are identical now. Okay. So our green function method or green function technique is working well for Poisson equation. Okay. In particular case of Poisson equation, our green function technique is working very well, and it will match the solution which you can find from electrostatics. Okay. So this is the way you can solve the inhomogeneous differential equation by green function method. So in other differential equations, like suppose for inhomogeneous wave equation or in any partial or exact differential equation which are inhomogeneous, you can perform the same method and you can solve these equations. Okay. But mind it, here I have chosen the natural boundary condition. The natural boundary condition is that this one. But if some finite boundary condition be given, then you have to make some slight change in your calculation or in the process of calculation to find the green function. Okay. So in the next classes, we shall discuss about the methods for finite boundary conditions which you can apply to solve the different types of inhomogeneous differential equations. Okay. And in quantum mechanics also, in your quantum mechanics course, you have to study about the scattering. Okay, scattering in spherically symmetric scattering center, which is known as the Rutherford scattering. So in quantum mechanics, while studying the scattering of a non-relativistic particle, you have to use this green function technique. So this green function technique is very important in further studies, both in electrodynamics and also in the quantum mechanics.